Okay, special triangles. We're going to look at just a couple of relationships that have to do with some special kinds of triangles, isosceles, equilateral, and right triangles. And specifically what we're looking at are some things like this. We want to be able to take situations with these kinds of triangles and the properties we're going to talk about that go with those triangles. And we want to be able to identify the values of angles, solve for variables, and we want to be able to prove congruence. We want to be able to prove congruence of the triangles using some special properties of these. So, what do we got? Use properties of these special kinds of triangles. Well, to do the stuff I just described. So let's look at one thing here. Properties of isosceles triangles. So if we look at an isosceles triangle, we've already talked about this a little bit. An isosceles triangle has, first of all, has how many congruent sides? Two or more. Good. At least two. Good. The classic isosceles triangle that we almost always talk about is one that has exactly two congruent sides. If an isosceles triangle is not equilateral, so it only has two congruent sides, then we can distinguish the legs from the base, right? The legs are going to be the two congruent sides and the base is the oddball. The base angles would be pretty obvious too, right? The base angles are the two angles that are adjacent to the base. Okay, and then the vertex angle would just be this other angle, okay, the oddball. Okay, so that's the anatomy of an isosceles triangle. What are some things we know about isosceles triangles? Well, the base angle theorem says that if two sides of a triangle are congruent, so it's isosceles, then the opposite angles are also congruent, right? So if these sides are congruent, then guaranteed the base angles are also congruent. Okay? That's the base angle theorem. We can also do a converse of the base angle theorem if it's convenient or necessary. And the converse just says the opposite. If a triangle has exactly two congruent angles, then what do you think has to be true? Yeah, good. The opposite sides would be congruent, right? So we could then say that those sides are congruent, which means it's what kind of a triangle? Isosceles. Good. Okay. Oops. Oh, got you.
So is the next test going to have a lot of proofs on it?
Not a lot. You know, some, but not a ton. Okay, so let's go ahead and try to prove this base angle theorem. So all we're trying to do here is if we are given that two sides of this triangle are congruent, then we want to prove that angles B and C are congruent. Okay, any ideas? What could we do? We have some suggestions. What do you think?
We could try proving that the triangles on each side are congruent with the corresponding parts.
Okay, we could try to do something like that. Are there any things that we get for free on this one? Okay, the middle, well, if we want to drop down a middle line here that bisects this angle, right? We can do that, can't we? We can add that, we can drop in, and we're free to do that. We haven't done any proofs like that yet, but we can. We can always add parts to a drawing if it's justified. So if I add an angle bisector here, well, what's that tell us? Because it's an angle bisector, what's that tell us about these angles? They've got to be congruent, don't they? I could break this then up into two triangles, couldn't I? You're on the right track here. In these two triangles, they would share this side, so what do I know about that? It's congruent to itself by the reflexive property, right? And this would just be definition of angle bisector, right? The fact that it breaks it into two congruent angles. And then we can add this little piece. And now if I look at those two angles, are they congruent? By what? By side angle side. And once they're congruent, Tyler, what am I going to do?
Corresponding parts.
Yeah, then I can prove that these angles are congruent by what's the, it's a tongue twister, what's the reason? CPCTC. Say that fast. Right? Yes, sir.
What about like the thing though, if it's on the last page, it says, you know,
Right, okay, right, but so,
Yeah.
what we're doing is we're proving that theorem, is what we just did. Yeah, so now we can use it.
Wait, what does CBCT stand for?
Okay, somebody tell me, what does CPCTC stand for?
What the hell?
Right here, Noelani, what's it stand for? That's right here.
I only got the first
Noelani's got the floor, what do you got?
congruent.
Corresponding of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent.
Yeah, so that's why I said-
Couldn't they just give it?
Well, that's the way they do it.
And then look, angles are corresponding to congruent.
Exactly, there you go.
Yeah.
Way to say the
Maybe because of
opposite.
triangles.
Way to say the opposite.
Okay.
I'm a genius.
Okay, so what else then? So we know that if a triangle is equilateral, then we can prove that it has to be equiangular by just using the base angle theorem, can't we? If you think about this. Can anybody, you tell me though, somebody explain how we could do that. Because I'll give you a hint to kind of speed this along. An equilateral triangle is also isosceles, right?
Yeah.
Okay, so how could we use the base angle theorem then to show that all three angles, that if all three sides are congruent, what we're really trying to show here, we're trying to show, this is a corollary to the base angle theorem, but I think on the list I just called it I can't remember what I called it. I think I called it the equilateral, equiangular, something or other. I just gave it its own name. I just made it up. But it's just a corollary, meaning it just kind of stems from this other theorem. But what it says is this. It says that if a triangle is equilateral, then it is equiangular, and vice versa. Okay, it's a two-way street. It's an if and only if kind of a statement. So how could we prove that though? How could we prove that if a triangle is equilateral, then it's equiangular by using the base angle theorem? Suggestions? Elton, what do you think?
Use it 3 times to prove that BC are congruent to AC, and then AB, or you can use the substitution.
Okay, so I think what you're saying is ignore that initially, maybe, right? So if I know that in this triangle these two sides are congruent, then the opposite angles are also congruent, right?
Yeah.
So the fact that in a triangle those sides are congruent implies that angles B and C are congruent. Just gotta do it one more time. Now let's ignore this one. How about? And we use the base angle theorem again, right? So now, if these two sides are congruent, then the opposite angles are congruent, right? And then what would be the last thing we'd have to say? If we know that angle C is congruent to angle B, and angle B is congruent to angle A, yeah, then they'd all be congruent just by what? Transit. Yeah. Make sense? Okay. Oops. Too far.
I think that angle is 60 degrees.
Do you? Okay, so find the value of x and find the value of y.
Thanks for giving us part of the answer.
Why though?
There. X and y.
Why is that? Why's on drugs?
Yeah, y is doing some weird stuff. Oh,
I should know the Prometheus force. There we go.
there we go. Okay, x and y. Okay, don't say anything out loud. Just stare at this for a second. See if we can come up with some stuff. Okay, Daphne, why does x equal 60?
Because if the two angles on the so the x and the one next to x, that would be they would be congruent. And
Okay.
Then the one at the top and then that one, so that'd be they all equal each other to create 180. So
Okay, and pause for just a second. So another way of saying that is because the blue triangle is equilateral, it's also equiangular, right? And so if all the angles are equal, we can do the algebra pretty easily. 3x equals 180, right? So x equals 60. Good, good. So we can do that. Let's add all those in. Okay. Thank you. Good. Okay, now what? Katie, any ideas? How am I going to get y? Can you tell me anything else here I could fill in?
The other part on the 60 right there.
What's that gonna be?
120.
Okay, 120. And there's something unique about this red, we'll call that the red triangle. What do we know about the red triangle? It's isosceles, so what's this one gonna be? It's gonna be y also. If that's y, then this is y, right?
30.
And so, yeah, so what's left over? So 2y plus 120 is 180, right?
Yeah.
So 2y must equal 60, right? So y is 30. Does that make sense?
Yeah.
Okay, good.
Yeah, that does make sense.
All right.
Good job, Lucy.
Yeah, I understand it now.
Good
Well, I
job.
was there on the day you started this.
I know.
Thank you.
Okay, so we got those.
You guys.
Okay, here's the other thing I want to show you. Our book doesn't do this, but a lot of books do. It's something you want to be aware of, because you'll probably see this again in math. So when we're dealing with right triangles, we can take our normal congruence postulates and theorems, our triangle congruence relationships, and we can truncate them a little bit. We can make them easier to deal with. Now let's look at how that works. So if we take, let's do a right triangle. Let's do two right triangles. Okay, so let's look at all the possibilities. Let's see what, for example, if I look at, if I look at side angle side. Side angle side, what would have to be the, what if I did this? What if I said that though that side's congruent to that side and that side's congruent to that side? We could show that those triangles are congruent by side angle side, couldn't we?
Yeah.
Right, because right angles are always congruent, okay? What we can do with this though, if it's a right triangle, we don't even need to go through the extra step of having to justify that, okay, this is a right angle and that's a right angle, so by the right angles theorem, they're congruent. We can skip that step, and instead, because it's a right triangle, we can call this the leg-leg theorem, okay? Because in a right triangle, we only need to have sometimes two things that are congruent, because the third thing is sort of implied. They're right triangles, so it's giving us some additional information about an angle already, right? Does that make sense?
Yeah.
So this is the hypotenuse, and these are the legs of a right triangle, correct? If the two legs of one right triangle are congruent to the two legs of another right triangle, the triangles are congruent by leg-leg, okay? So we don't have to, you see why that's a little bit easier? If we were writing this out as a two-column proof, if we wanted to use side angle side, we'd have to add an extra step to justify that the right angles are congruent, right? This way we don't have to. See that? Our book doesn't even bother with it, but some books do, okay? What about, let's look at a different one. What if we had, let's see, I could be smarter about this. Let's see.
To be honest.
So, isn't that beautiful?
That's why I just said that.
Right,
E for effort, but she's not in the grade book, so you actually failed, that's fine.
Okay, now I won't have to keep redrawing that over and over again. Okay, so let's do this. Let's try something different though. This time let's go. Hey, what about that? if I were not using, now, using our old methods, how are those congruent? Okay, so angle, side, angle, what do you think that's gonna become?
Wait,
Hey,
To leg angle. Okay, that becomes the leg angle theorem. Right, we've got a leg and an angle, and we should say acute angle, right? When we say angle, because we've got a right angle that's given, the other two angles in a right triangle are both acute, right? So technically, we should say if a leg and an acute angle of one right triangle are congruent to a leg and an acute angle of a second triangle, right triangle, then the right triangles are congruent. So we'd call this leg angle, or wow. Okay. Okay, what if we do, what else are we missing here? What if we did, what else could we do? There's gotta be one other one we can do. What am I missing? Leg angle we did. Oh, I know what we missed. I got it. I know what we missed. I think we did this. So we did. Something like that.
Don't we just do that?
Not quite. What's different about this one? So this would normally be what? Angle, angle, side.
wait, so I don't get it, why? Side angle?
Okay, but now how would we label those in a right triangle? Hypotenuse, angle. Yeah, so it'd be HA.
I get it.
Okay? See what I'm saying? Okay, do we have to do that? No, we could just use angle, angle, side, but hypotenuse angle is a little bit easier because we don't have to, once again, we don't have to justify that third piece. Opposite the right angle range.
Oh, I was so confused, because sometimes when you say hypothesis, you say hypotenuse.
Okay, make sense? Okay, well, ask a question. If it's not making sense, ask a question. Does it make, maybe the question is, why are we doing this? Kind of. Okay, once again, the only reason we're adding these additional relationships is because they're a little bit easier to use. They only require 2 congruences and not 3. But so far, I could do this. So far, we could say that these are essentially interchangeable, right? If it happens to be a right triangle, we can take advantage of the red relationships. If it's not a right triangle, we got to use the blue ones, right?
Yeah.
Okay, but there is one new thing that comes out of this that we otherwise don't have. What about this one? So those are kind of take them or leave them a little bit. But this one, you only want to take it because it's new. What if we did this? Okay, so if we did. Okay, now, what would that one normally be?
Angle, side, side.
Yeah, that would be angle, side, side. Okay, that's a problem, right? We know right away that one doesn't work, right? Angle, side, side's no
You
good.
can read it the other way.
Thankfully.
Side, side angle.
Should write it probably as SSA instead, right? But we know that because that one could be made embarrassing, that was the one, the math gods spared us that misery and they got rid of that one. But,
in English.
so this one, my point is, this one does not work for a non-right triangle, but it works for a right triangle. That's what's interesting about this. So this one actually does become HL, hypotenuse leg, which is a legitimate, very sneaky. That one becomes HL. Okay, so does that make sense? Do you see, does everybody get that? That this is one that normally wouldn't work, right? That's one of our forbidden ones. That does work for a right triangle, okay? All right, so Okay.
We could spell it that way.
H-L.
No, we're not gonna. There. Okay? So, what about this one?
What's at the end of all the angels?
What's that?
Why does the angel keep on?
Doing what?
Where?
Oh, over here?
Yeah.
Oh, they skip over.
Do what?
Hey, how about this one? Yeah.
So does that have to be right? Oh, I heard that.
Hey. Okay, what about this? So now we got a three-dimensional picture here. We've got this television antenna. So the television antenna is this middle segment. So segment AE is the television antenna. We've got these, I guess these are probably guy wires that are holding this thing up that are right, so it's sort of three-dimensional. They're attaching to the ground on three sides to support this thing. Okay, we want to know here,
Oh, this is like a TV channel.
yeah, kind of like a TV tower thing, right? So could we prove that those three triangles formed by the guy wires and the antenna and the ground, the flat ground, that those are all congruent?
Yeah.
Okay, how could we?
Well, you get out a big ruler.
You got a big ruler. Okay,
And
Okay.
they're all perpendicular to that line, aren't they? All 90 degrees.
okay, there we go, good. So we could add something here, couldn't we? They're all perpendicular to the ground and to, right, does that make sense?
Yeah.
So these are all gonna be, that's pretty bad, but you get the idea, they're all mutually perpendicular to the ground, okay? Now what?
And then the, yeah,
That's congruent to itself.
Okay, they all share the antenna, right? So they have a common side, so that's congruent to itself. And now what's the relationship that allows us to prove these congruent? HL. Yeah. Okay. Good. All right. Okay. Can we, let's see. What do we want here?
Which means that,
Okay. Could we,
all the angle bisectors of BAC.
Oh, the green line.
Oh, it's already drawn there, but we don't know if it's.
okay, yeah, it doesn't look very good, does it? Okay, can we prove this? So all we're given here is that angle B is congruent to angle C. So we're doing the converse of the base angle theorem, right?
Yeah.
We're just proving it. Can we prove that side AB is congruent to side AC? What do you think? Some ideas here.
The base angle converse.
We're proving the base angle converse.
Okay.
Because remember, the base angle theorem says if the sides are congruent, then the base angles are congruent. Kirk's got an idea. Get us started.
Well, I was just wondering, but on the assignments, we can use the basic approach just to, on this, like.
Oh, yeah, you guys, right. All we're doing here, and this, you'll do this a lot in math, we're just gonna prove, you guys can use the base angle theorem and the base angle converse. We're just gonna prove it, assuming that we're the first people to ever do it. Okay? So what do we think here? Gabe, tell me something that might be useful. And, go ahead.
Segment in the feminine side like this, but those.
Okay, good. So we're gonna drop down an angle bisector, right, for angle BAC, and that's congruent to itself. So there's a piece of congruence that we can get out of this. Okay? And what else? What else? Eliminations. Okay, we know these are congruent, and then if this is an angle bisector, this is what you're talking about, the green ones? Okay, if it's an angle bisector, then it's cutting angle BAC into two congruent pieces, so probably we'll do something like that maybe, right?
So angle.
Okay, so now by angle side, we can show that the two triangles are congruent, right? Okay, and if they're congruent, then how could I show that this is true?
CTC.
CP, CTC. right? Okay,
The one thing
Just say C a bunch of times, it'll probably pick up what you said.
okay, okay. Let's say, I'm gonna make one thing to make it a little harder.
I thought it was C, B, C, D, those always are
So those aren't congruent?
Okay, hang on. So now, I'm gonna make this different. So I'm gonna say, let's say we can't use that fact. And let's say instead of calling this an angle bisector, let's just call it a perpendicular to the base.
Oh, you can do it like.
Oh,
Okay.
then it,
We could use pop.
Okay, so we're gonna do that.
On
it's
both
also
sides.
on the
Okay.
other side.
Brooke, do you see a way that we could do, now, this is what we're trying to prove, so let me erase that. You see a tricky way here? If all we're saying now is we're dropping down a perpendicular to the base, and really what we would call that in geometry, just so you kind of get the language, we would call that an altitude, right? Because if this is the base, you'd want to think about it as being set on its base, and so this is an altitude, right? You're dropping it down from one vertex down to the opposite side is an altitude, okay? And it's perpendicular, okay? Drop it down perpendicularly. So that's a right angle. Any ideas? Okay, so we don't, but now ignore that, we don't have that anymore. Now all we've got is just, this one is obviously congruent to itself. That one's still fair game. And we know we're given that these two angles are congruent.
We know that the two right angles
We do, you're right.
are both sides.
So these are both, so I guess what you're saying is these are both right triangles, aren't they?
Yeah.
Right? So if they're both right triangles, angle, angle, side, sure, but then if we do that, and that's fine, we could do that, but then we'd have to add the additional step that these angles are congruent. Let's say we're getting really lazy and we don't want to do that. What's it gonna be? Yeah, LA, right? Leg angle. Okay,
It's the Dodgers theorem.
right? There you go. Right, because we got a leg of the right triangle and an acute angle congruent to a leg and an acute angle of the other right triangle. Does that make sense? So we could also then take a shortcut and just use LA. Okay? Good. Okay. What are we at? 20? Okay, so
We don't have any time left.
Oh,
We're good now.
pretty cool, huh?